Hi, this is OPC for Andover Controllers. In the first half of the presentation, I'll cover some OPC background, like what is OPC, what's an OPC server, what's an OPC client, and how do these two things talk to each other. In the second half of the presentation, I'll cover Andover's specific OPC server. If you have any questions, you can email me at sen.can@4itg.net. Okay, let's start off with an example of an OPC client application. This is a Visual Studio C# application that I wrote running on a Windows XP box on the network. There are no Andover Controls applications of any sort on this box. I do have an OPC server out on the network. Along the left-hand side, you can see my OPC items, or tags. For example, I have the telephone room and its value. This is going to tell me if the telephone room door is locked or unlocked. I also have its door switch. The switch will tell me if the door is open or closed. I have some other miscellaneous points, as well as a discharge air temperature, space temperature, and a space temperature set point. If I click the read button in the application, I can read any of these points from the Andover system live. In this case, I can see that the current value of the telephone room is unlocked and closed. If I switch over to another box on my network that's running Andover Controls, I can see that the phone room in fact is unlocked and closed. If I refresh, I can confirm that those are the values. I can also change my door to locked and then switch back over to my OPC client machine and see that when I press the read button, it updates to locked. I can also put a value in to this point. For example, if I put the value 60 in and write it to the door or to this tag, I will unlock this door for 60 seconds. I'll switch over to my Andover Controls Cyberstation again. In Cyberstation, I press refresh, and I can see that in fact the door is unlocked now. Back in my OPC client application, I can do a subscription. This is going to update these points every 5,000 milliseconds or 5 seconds. Once I press the subscribe button, you can see that these tags begin to fill in. They'll continue to update every 5 seconds. I can change the set point for this room from 71 to 71.37, write the value, and you'll see that it updates automatically. If I switch back to my Andover Cyberstation machine, find the point and open it, I can see that in fact the value is 71.37. I'll change the value here to 70.99, apply it, and then switch back to the other Windows machine running the OPC client and confirm that the value updates. Alright, so that's a really simple example of OPC communications. Most often it's going to be something a little bit more complicated than this. Maybe bringing together data from multiple systems, data archiving for statistical analysis, or even real-time loop tuning. But what it shows is that an application can easily plug into an existing control system. And more importantly, it can do that without knowing the vendor-specific technical protocol for communicating with those systems. The same application can communicate with any OPC server on the network. Andover, Allen Bradley, Modicon, and so on. And it can do this without any changes to the core application. Originally, OPC was called OLE for Process Control. And even though the name OPC still looks like an acronym, the current stance by the OPC Foundation is that OPC is no longer an acronym and should just stand on its own as OPC. The name itself arises from OLE, or Object Linking and Embedding, a Microsoft technology for sharing of data between applications, hence the original name. OPC is an open standard for system interconnectivity. The standards themselves can be read online at www.opcfoundation.org. In a nutshell, though, it defines a common set of programming interfaces, methods, and properties for software development. And as I said before, it's based on Microsoft's OLE technologies. The standardization itself is key in minimizing software development costs when various vendors are involved. So a sort of parallel example that I think gives a really good overview of what OPC is trying to achieve is early versions of the Windows operating system and printer drivers. In those early versions of Windows, a developer had to not only write their own code, but a bunch of printer drivers for specific printers that they anticipated their users using. As you can imagine, this would get expensive quickly and also very time-consuming. On the flip side of the coin, it locked users into only the printers that their software manufacturer provided for. And those software manufacturers weren't too eager to implement details for some obscure printer that only a few people used. But in later versions of Windows, Microsoft fixed this by decoupling the hardware from the software. Essentially, they left the vendor-specific hardware details, or essentially the driver, to the printer manufacturers and allowed the software manufacturers to focus on the software itself by creating a standard printer interface. Essentially, this is what OPC aims to provide for process control. Decoupling of hardware from software and letting the user choose best-of-breed products. For example, historians, SCADA packages, loop tuning, or trending software. Whatever they want, with whatever hardware they want. At least that's the promise. The original OPC specification was released in 1996. The latest, UA, or Unified Architecture, was released in 2007. So let's take a look at data sharing from a bird's eye view of the network. Along the top, I have some consumer applications. These are things that request data from our control systems. Things like archivers, reports, field HMI, SCADA packages, let's say Wonderware in this case, enterprise resource planning, maybe SAP, web applications, and maybe even some Excel spreadsheets on user desktops. For our control systems, we have Andover, which provides building automation, HVAC, and security. And for process control, let's say this is a plant where we're manufacturing something, we have Allen Bradley Slick 500s. So what happens is that a programmer programs each of these data consumers along the top to go out to the field controllers and get the data that the application needs. This, of course, isn't always so straightforward, since there isn't always a published protocol for getting that data. Also, as you can see, the control systems themselves can become bogged down with responding to requests for data from the applications. So the owner of this network would have some common data exchange requirements. They'd want to minimize direct requests to their field controllers. They don't want the field controllers busy with responding to data requests from the consumers and not able to do the control job that they were intended for. Ideally, I'd also want to increase my efficiency. One way that I might go about doing this is by grouping points. For example, points that don't change that often, I could put those in a slow group that's pulled, say, every 5 seconds. Mission critical points, maybe I want those quicker, let's say every 500 milliseconds. As you know, access to infinite LAN and RS-485 networks is often slower, so in that case, it would be acceptable if it cached a point for me, as long as it provided the timestamp and the quality of data. It would also be ideal to be able to provide a common interface for application data needs. In this way, we could minimize implementation costs for new software development. We wouldn't have to reinvent the wheel each time we have a new data consumer come on the network. So we now arrive at the need for something called an OPC server. This is a program or a service running on a Windows box that provides a standardized access method for data from particular devices or series of devices. In the case of our example, this would be Andover Controls and Allen Bradley Slick 500s. We could also interface with DCSs, BACnet, Excel, ODBC, etc. In fact, there's OPC servers for almost all varieties of control systems hardware. And now, since we have the definition of an OPC server, it wouldn't be complete without the concept of an OPC client. These are programs that retrieve and optionally set data from an OPC server. Examples are HMI, SCADA, Historian, live neural network models, and Excel. The OPC client communicates with the server via something called interfaces. While the actual implementation of the programming of the OPC server varies significantly, the interfaces that it exposes to clients is always the same. This allows for a standardized way of any client interfacing with the server. Finally, we determined earlier that we'd like to use groups as a way for prioritizing and organizing our data collection. Each group can be enabled and disabled as needed. It also has a configurable update rate. As an example of two groups, we might have space temperatures, which are refreshed every 1 minute, and door statuses, which are refreshed every 1 second. In each group, we can define field points and attach them to the group. So let's revisit our network, this time with OPC data sharing in place. In this case, we have two OPC servers, one for Andover Controls and one for Allen Bradley. Each of our data consumers makes its request to the OPC server instead of directly to the control system. So what we end up with is a controlled and standardized way for each of these applications to communicate with the field controllers on both the Andover and Allen-Bradley networks. If we chose to, we could even have the Andover and Allen-Bradley systems communicate with each other via the OPC servers that are now in place. So of course, Andover Controls does